So as I said, we're going to start with ceiling systems, looking at some examples of how we're going to use computational design. But we're also going to talk about facades and other kinds of just physical manifestations about what we can do with computational design techniques. And the place we start is with the project that we're going to do in this module, and that's to create a responsive ceiling system, dynamically responsive. We change the shape of the line, and the ceiling system responds to that. The shape of the line being that blue line behind my head, or in the section view here that you can see with the three dots on it, you can change the shape of that. That could represent the path through a space that people might be taking. And then the ceiling responds to that, wherever there is an element, a ceiling element, its distance from the line, the nearest point to the line is calculated, and a distance or a length is assigned to that pattern. So the further any box or ceiling panel is from a line, the longer the panel is, the closer it is, the shorter it is. And you could change that around to be the inverse if you wanted, because this is just a manipulation of math. So we have a dynamic way of creating kind of a decorative or dynamic kind of ceiling system. And it's nothing new. This is an expression of the same thing with more symmetry, with the idea probably for acoustical performance at the same time. And this might be something that you wouldn't normally think of. This is on the National Mall. This is about the, I click into that and show you what it is actually. Gone Too Soon Society's Cage is an art exhibit about systemic racism. And the idea of the length of those is a response to some kind of a data set, the length of those. So you could also be associating this now not with a line on a floor, but maybe with the weight of statements. This could be actually, I'm not sure what this was, but states in numbers of lynchings or something horrible like that. And so you could be taking the data on a chart and correlating it to the structure of a ceiling construction. And then more artistic kinds of ideas about what you could do. This is a ceiling system, probably through what people considered a really boring or uninteresting space, a mall space, and they wanted to activate it. And so the idea of using computational design, inputting images, color coding, then taking that image data and assigning colors to it, and shapes to the patterns, and flows and distortions, all could be defined. You could do it all manually. There's nothing actually wrong with that except for just the incredible complexity of it. Or use mathematical techniques that we're going to learn in order to generate these shapes and forms for us based on simple mathematical instructions. So that covers the idea of our ceiling plane. And now I have a couple of examples of computational design and really dynamic facade design based on some of these ideas. So here we have the Gates Hall on the Cornell campus. This is by Morphosis. I'll show you another project by them shortly. But we can see these panel systems on the side of the building, and they seem to be reflecting either the movement or wind or something along that system, kind of capturing what the dynamic movement of air around a building in a visual form. It could have other references. It could have to, obviously this is about data and information, and so it could have other kinds of meanings to it. But obviously a lot of very detailed manipulation of panels and plane systems, and so really aided this kind of design is really aided by the idea of being able to use computational design in order to take a set of data about the motion of wind or distortion of panels with respect to attractor points or whatever, in order and then to be able to say this panel will be this shape, be mounted on this angle, stick this far off from the building, and now we can create construction documentation for the fabrication of these components. So here we have a close-up of those. And they're also performing other functions. They're not just completely decorative in nature. They can be used to control solar insolation, solar gain. And so if we were to look back at this, this might be aligned with a certain time of day and a projection of the sun in order to create the maximum amount of shading effect on the building. And computational design obviously could, the idea of the facade moving to the inside. So here we have just an interior view and some kind of manipulation of the panel systems on the interior of the building. And following along with that, this is Morphosis. This is Emerson College in LA. So here we have this kind of interstitial space between two buildings, and then we have these panels that are bent and shaped to create this kind of a dynamic facade on the interior of the building. Once again, morphosis kind of closely aligned with this idea of of using computational design, and a couple of projects that play it out. Here's another, this is actually a factory building by Zahner, a metal manufacturer in the Midwest, very significant metal manufacturer for facades. And so what they did is they took the idea of a cloud system and split that curvilinear shape up and then played it out into a panel system that was fabricated by a CNC machine in order to create this kind of undulating facade. And it's not to say you absolutely need computational design to do this. There are other ways that you can manipulate this data set by implying surface shapes on other ones and then dividing them off. But the advantage afforded by computational design is the ability then to take that shape that you generate in a panel and then to manipulate it back into a flat planar surface that you can use to drive a numerical cutting machine or a laser in order to cut out that sheet shape for the panel system. And once again, it's not always about, and this is just an example of a building that I would say probably didn't need computational design with much of the same effect. There's no kind of unique differentiation of the panels, but still a very powerful kind of second layer of sun shading and solar gain control to the facade element. And like I said, this could be easily applied to any kind of curtain wall panel without the need of using the computational background for that. Now, another way of looking at this is actually this kind of using the math in a dynamic way to actually change the shape of things or the look of things. And so here we have an acoustical panel system, and it actually changes its shape in order to respond. And I'll click out to the web link here. A resonant chamber that is acoustically responsive envelope. So here we have a panel system that actually is hinged together. So if we were to roll down here, you could see these have perforations in them for better acoustical performance of sound absorption. And then we have hard surfaces actually to create better reflecting surfaces. And then by manipulating the shape of that surface with these actuators behind, we can actually configure this to be either more reverberant or more sound absorption, depending on what kind of performance we would want out of it. And so in this case, the feedback loop could be dynamic, where a microphone is listening in the room or multiple microphones, and then making a decision on whether that sound is too reverberant or too absorbing sound too much, and then shape those panels and then listen again to find out if it's made the right kind of acoustical correction to that space. So, really, once again, not always dependent on that one single idea of computational design, but these are the kinds of things, the world that is opened up when we start looking at things both in a dynamic way and a mathematical way. And this is one, and I have a little case study on this one, and we do a little bit with it, is the idea of mapping an image to a surface and then maybe cutting or manipulating it in order to kind of map that image onto the surface. So here we have a building in New York City that's an industrial building trying to recreate the heritage of the site. And so we see these bridges and gantry systems as an image. Now it is holes cut through sheets of aluminum panel. And so it works in two ways. It's both a visual element on the building, but it's also a way to cut solar gain through the glazing system. So we're controlling heat gain within the building. And then there's just tons of, if you go and explore this, there's tons of software or manufacturers who deal really strongly with the idea and power of what computational design can do for the creation of the built environment. And this is actually taking data. I'm going to play this, and I might pause it if the sound isn't coming through. Let's see if we get a soundtrack. So that took me a second to get to that. Just using data to create a surface. So the shape is based on this data of mobile device sales. And then they mapped that, they took all of that data set and then mapped it out into some kind of a pattern. And I'll show you a case study where I've done somewhat of a similar thing. And then finally, my last example here is actually something that's happening in Buffalo, New York. This is the Albright Knox Art Gallery. The image above is the finished rendering of a roof covering for what was currently an open air part of the museum. And the artist, primarily the designer, the roof system, while architectural, was designed by um, an artist, probably with architectural background. But the idea here is this is actually something, once again, that could really be accomplished without computational design, but is further advanced with the tools. So here we have a curvilinear surface coming down into what looks kind of like a tornado in order to support that roof system. And then we have a secondary set of a grid system that is supporting a random arrangement, or what looks like to be a random arrangement of mirrors reflecting the space back on. And so this is well within the realm of projects that you could, as architects, be involved with. And these are happening right on our doorstep.